In this lesson, we will study about two concepts. First is about the user-defined functions known as recursive functions, and second is the concept of memoization, which is also associated with user-defined functions. Let's start with recursive functions. Recursive function is a function which calls itself. We know a user-defined function can call any other user-defined function, and there is a possibility that a user-defined function calling itself, and that is known as recursion, and the function is called as recursive function. Of course, the first question arises in mind is that why a function would call itself. Let's see that with examples. Here I have defined a function to find the factorial of an input number, although we have factorial function in math module, but the purpose here is to understand the concept of recursion. This function at the moment is not recursive function, but let's first see its logic. Logic is very simple. For factorial of a number x, we need product of all integers from x to 1. Here the for loop is generating those numbers and we are calculating the product. Here I have called the function to find the factorial of 4 and 5. Let's run the code and the output is correct. Factorial of 4 is 24 and factorial of 5 is 120. Now I will write a recursive function for factorial calculation. But how do I know that I can have a recursive function for a factorial calculation? See this formula of factorial of a number x. If you see this formula, to find the factorial of a number x, we need to find the factorial of number x minus 1. And that is the indication that we can use the recursive function. If still it is not clear, instead of factorial symbol, let's define the formula as factorial function. Fact of x is equal to x times fact of x minus 1. To find the fact of x, we need to calculate the fact of x minus 1, and that means a function is calling itself, and that is recursion. Fact of x minus 1 will be x minus 1 times fact of x minus 2. Again you can see the recursion. Then fact of x minus 2 will be x minus 2 times fact of x minus 3. And so on until we reach this limit of fact of 1. And fact of 1 is 1 times fact of 0 and fact of 0 is 1. Or you may also end the process at fact of 1 as 1 without going till fact of 0. So for fact of 0 or fact of 1 we do not need to call the function and the answer of fact of 0 is 1. And here the successive calls to the fact function will stop. So if we can write the general formula of the factorial of a number x with the assumption that x is a positive integer, then we can say that factorial of x is x times factorial of x minus 1. And if x is 0 or 1, factorial answer is 1. Now we will see that in coding that instead of using the for loop to find the product, we can use this recursive definition in our user-defined function. We will implement the definition as it is, like if input argument x is 0 or 1, the factorial answer is 1, so we will simply return 1. Else means it is some integer greater than 1, so for that case we can return x times fact of x minus 1. So we are calling the same function fact inside the body of the function, and hence this function is a recursive function. Let's see the output of factorial of 4 and 5 and we get the correct output. We call this case as the base case because this is the case which is not calling the function again, and recursive calls will end when this case is achieved. And this case is a recursive case because it is calling the function again. We saw that function is working correctly, but let's see the code execution step by step to see how actually answer is calculated by the recursive function. I am placing a breakpoint here. Function is being called with the input argument 4. X is 4, so the condition is false. Interpreter will move to the else block. Here the function is called on x minus 1, which is 3. So function is called again and interpreter will execute the function with input argument 3. Again the condition is false and else block will be executed. Now the function is called on x minus 1, which will be 2. This will continue until we get fact of 1 and finally the result. But I guess even with this step-by-step execution, the whole scenario is not clear since the same function was being called again and again and we really did not get the idea how the answer 24 was calculated. So instead of debugging tool of the IDE, I will try to explain the working sequence on my slides. Here we have the same recursive function shown in yellow color and on the right side we have the program calling the function on value 4. Since the function will be calling itself again and again and it's hard to track what's happening, so for better understandability, I will show the duplicate copies of the same function so that instead of watching the sequence on same one function, we are assuming that it is a different function with the same name. Remember, it is not actual Python program, it is just a presentation slide here. And in actual we have just one function, but here I created multiple copies just to see the sequence clearly. So now when we are calling the function on value 4, the interpreter will move to the function body with x as 4. I have placed a yellow anchor point here to indicate that it is waiting a value to be returned by the function in yellow color. Now coming to the current point of the interpreter, the condition is false for x equal to 4, so it will jump to the else block. Here it is calling the function fact with the value x minus 1, which will be 3. So we can say that this function has called another function on value 3, which in reality is the same function, but we will assume that it is a different function shown in the blue color. And I have placed a blue anchor sign here to indicate that this point is waiting a value to be returned from the blue function. The blue function is called on value 3, so this condition is false. Interpreter will jump to the else block. Here this expression is executed as 3 times fact of 2. Now that's calling the function fact again, so interpreter will jump to the fact function in green color with value of x as 2. And there is a green anchor point expecting a value to be returned from the green function. Value of x is 2 for the green function, and hence the condition is once again false. Interpreter will jump to the else block where the expression 2 times fact of 1 is being evaluated. So once again fact function is called and it is now the brown color function, and I have placed a brown anchor here to indicate that it is expecting a value from the brown function. Now x is 1 in the brown function, and this time the condition is true. Hence interpreter will enter into the if block where it is returning the value 1. This time no new function is called, and this function will return the value 1 to the point where it was called, which is the point of the brown color anchor. So interpreter will move there and value of fact is 1, and this expression will get evaluated to the value 2. Now the value 2 will be returned by this function to the point where it was called, which is the green anchor point. Value returned by the green function is 2, and hence this expression will get evaluated to 6. And that value of the blue function will be returning to the point of the blue anchor. Value returned is 6, and this expression will get evaluated to 24. And it will be returned to the point of the yellow anchor where the function was called first time. And you can see the value returned is 24, which is correctly the factorial of 4. So you can see how recursion worked, and in reality these are not multiple functions but the same function is called recursively. Now we should compare the performance of the recursive function and the simple non-recursive approach, but we will first see another example that can be solved using the recursion. This example is about Fibonacci series of number. It is a series of number that starts with 2 ones, then each next value is generated as sum of last 2 values of the series. For example, if we add these 2 ones, we will get 2. Then to get the next value in the series, we will add the last 2 values and sum is 3. Then we will add these 2 and the next value is 5. And so on, each next number in series is sum of the previous 2 values. I will suggest to search for some magical relation between the Fibonacci numbers with different natural phenomena. You can easily find interesting facts about these numbers with many natural phenomena. Anyways, we can assign index to the Fibonacci values as well. The first row is the Fibonacci numbers and second row is the index of the series. I have started the index with 0. So I want to relate the index number with the value of the Fibonacci number. It's very simple. We can express that with this relation. N is the index value and f of n will evaluate the Fibonacci number at index n. And it's simple that if the index n is 0 or 1, the value of Fibonacci number is 1, and for any other index n, the Fibonacci number is f of n minus 1 plus f of n minus 2. You should easily observe that this is a recursive definition. To find the function value for n, I need to evaluate the same function for n minus 1 and n minus 2. This is the base case and this is the recursive case. So let's now code this as a recursive function. It should be very simple to understand here. Let's find the Fibonacci number at index 5, which is 8. And we get the correct result. For index 6, it should be 13. Now let's move to the important discussion of comparison of the recursive function and non-recursive function. If you see this recursive function for Fibonacci series, you can see the code implementation is very simple here, intuitive to what we have the definition of the Fibonacci series. Similarly, for the factorial function, the recursive function is very close to the actual definition of the factorial. So the advantage of the recursive function here is that it is simple to implement. If you are not convinced, let's try to implement the Fibonacci series using the non-recursive approach. Let's see what can be the logic to get the Fibonacci number from the index n. Suppose I want to get the value at index 5, which is 8. The starting two numbers are 1s and we can define two variables a and b both having the value 1. Now I should update the value of a and b against this pair of the numbers. In this pair, the first number is the second number of the previous pair and second number is sum of the previous values of a and b. So I should say that I should make the value of a as previous value of b, which is 1. Keep in mind it's not the programming statement I have written here, but just the algorithm that I should get the previous value of b. And then b should get the sum of previous values of a and b, which will be 2. So values of a and b are updated. Now I need to get the next pair of the series, and the logic is again same. A should get the previous value of b and will become 2, and b should get the sum of previous values of a and b and it will become 3. Then again for the next pair, I will repeat the process and will get the updated values of a and b. A becomes 3 and b is 5. I need to do this one more time and b will be 8, which is the value we were interested to get. So for index 5, I started with the initial values of a and b and then I did this update process 4 times. So in general for index n, I will have to do the update process n-1 times. So this can be the code. This is the starting values of a and b and then these are n-1 iterations and here I am updating the values of a and b. After the complete iterations, b will have the Fibonacci number against the index n. Let's implement the non-recursive function here. This is the logic we just discussed. Another thing I will mention here is that see this loop variable I. This variable is not used inside the loop body for calculation and is just controlling the loop iterations. In such case, it is a convention to use underscore as a loop variable. Let's run both recursive and non-recursive function to get the Fibonacci number for index 6. Result is correct with the both functions. You can see here the logic of recursive approach is much simpler as compared to the non-recursive. But it's not enough. Now we will compare the two functions by their performance. So let's find the first 100 Fibonacci numbers. For that I will use the for loop. And first I will use the recursive function to find the Fibonacci numbers. Let's run it. We're getting the result. It's Fibonacci number 31, then 32 and so on. Fibonacci numbers are being calculated, but see that as we are moving ahead in series, the time taken by the program to compute a Fibonacci number is increasing. I guess it will take few hours till it reach the 100th Fibonacci number. So I will terminate the process by pressing Ctrl+C keys. It was very time taking, and now let's test the same thing using the non-recursive function. And you see that it took just a blink of an eye and we got the result. So if we compare the two approaches, you can see that recursive approach was intuitive in terms of logic implementation, but its performance is too bad as compared to non-recursive approach. Yes, apparently that's what we found, but wait for a while and now we will study about the concept of memoization. And by that we can improve the performance of any user-defined function when that is being called repeatedly, whether that is a recursive function or non-recursive function. But it is especially important when the function is recursive function. Before I discuss about memoization, what do you think is the reason of such bad performance of the recursive function in the Fibonacci example? Let's see how Fibonacci number at index 4 is calculated in the recursive approach. We know Fib4 is Fib3 plus Fib2. How this expression will get evaluated? This needs to calculate two terms and then we'll add the two. It will first go to calculate the first term, which is Fib3. So it will move to the function and Fib3 is Fib2 plus Fib1. Now this expression needs to calculate two terms. The first is Fib2. So it will first go to calculate Fib2. That is again having the two terms. So it will go to calculate the first term, which is Fib1. And this time the answer of Fib1 is 1. So now it will return the value 1 to the above node where it was called. So in this expression, the first term is evaluated to 1. So interpreter will now compute the second term, which is Fib0. For that it will call the function Fib with the value 0 and the answer is 1. So 1 will be returned to the above node. Now both terms are calculated and this expression will evaluate to 1 plus 1 equal to 2. From here, this value will be returned to the above node, and there is one more term in that expression. It will go to the function again and will get the value 1. This expression will get evaluated and will become 3, and this value 3 will be returned to the above node where actually the function was called originally. Over there we got the value of the first term fib3, but still we have to calculate fib2. So it will go to the function again and will evaluate that as fib2, which is fib1 plus fib0. So once again fib1 will evaluate to 1 and will be returned here. Then fib0 will be calculated, returning the value 1. This will become 1 plus 1 equal to 2 and will be returned to the top node. Now both terms have been evaluated and the sum will be 3 plus 2, which is 5, which is the answer of fib4. So you see how many times the function is being called, and at the moment n is just 4. What if n is 100? There will be so many nodes and so many calls to the same function. By the way, can you guess how many will be the nodes of this algorithm for a general value of n? I have shown the calculation with right and left branches. So can you see that if n is 5 instead of 4, then this whole structure will be the left side of the node n equal to 5. So with every next value of n, there will be almost double nodes. I'm saying almost double and not exactly double because left branches are smaller than right branches. And in general, we can say that for n, there will be of the order of 2 to raise power n nodes. Not exactly 2 to raise power n, but of the order of 2 to raise power n. Again, because left nodes are smaller nodes, so it will not be exactly 2 to raise power n. Let me tell you about the complexity or the order of some algorithm. We define the complexity of an algorithm, which can have different types, but most commonly is time complexity of an algorithm, which refers to the number of calculations needed for an algorithm. More number of calculation means more time. Less number of calculation means less time. Here we can declare this calculation or this calculation as one calculation since it readily gives the answer. Then complexity of this algorithm means how many such calculations are required if we are computing the algorithm for input n. As we said earlier, that for each next value of n, there will be almost double nodes in this structure, and mathematically we can say that it needs around 2 to raise power n calculations. We represent that as O of n equal to 2 to raise power n, where O represents the order and we also call it as big O notation. You should have in mind that it does not mean that there will be exactly 2 to raise power n number of calculation, but it will be of the order of 2 to raise power n. Or you can say that the number of calculations and hence the time required is proportional to 2 to raise power n. It might be quite less than 2 to raise power n, for example, for some algorithm. If the exact number of calculation is 0.1 times 2 to raise power n, still we call that the order of the algorithm is 2 to raise power n. And if some algorithm has the order 100 times 2 to raise power n, still we call that the order of the algorithm is 2 to raise power n, since in both cases the complexity is proportional to the factor 2 to raise power n. Just for a little more discussion on general concept of complexity of an algorithm, here I have shown 3 graphs as order of 3 algorithms. This one is order of 2 to raise power n, and you can see as n increases on the x-axis, the complexity is increasing exponentially. We also call that this complexity is exponential. Then this is order n complexity, meaning that as n increases, the complexity increases linearly. We call it as linear complexity. Then what about this order 1 complexity? It is a constant complexity, meaning that no matter how big is n, the complexity is constant. Can you think of some algorithm with a constant order or order 1? Finding a number is even or odd is order 1 algorithm. No matter if you want to find 2 is even or odd, or you want to find 2 million is even or odd, you need just one calculation, which is finding the remainder after division by 0. So that is a constant number of calculation for any value of n. So now coming back to this Fibonacci algorithm, where we observed that it takes a lot of time and is having the complexity 2 to raise power n. Now we will see that we can use the concept of memoization to improve the complexity of this algorithm. So what is memoization? On Wikipedia we find this definition. In computing, memoization is an optimization technique used primarily to speed up the computer program. How? By storing the results of expensive function calls and returning the cached results when the same input occurs again. Now let me explain that. Suppose that you have a function doing some calculation and returning a result. Suppose that the calculation takes sufficient time for the execution, say in minutes. Now further, suppose that in main program, we need to apply this function on different inputs, and that's what we are doing here. See this where we have applied the function on the value 10, and let's suppose the function took 2 minutes for the calculation and returned the value 1.678. Now over here the function is again called on the same input value which is 10, so of course the function will take again 2 minutes for the calculations. And that's where we can play intelligently, in a way that when function computes some output against some input, we can save that input-output pair in our program. For example, this pair in case of input 10. And next time if the function is called on the same input value 10, then instead of doing the calculation again, we can pick the stored information from our program. And instead of 2 minutes, that could be done in less than milliseconds or even less than that. Now you can understand this statement that storing the results of expensive function calls and returning the cached results, meaning the results we have stored in the program when the same input occurs again. Now how can this be helpful in the recursive Fibonacci algorithm? You can very easily see that many repeated calculations are being done here. So let's use the idea of memoization to improve the complexity. As we said that we should store different input-output pairs in our program whenever a function is called, and I think dictionary is more suitable for this case. The keys will be the input and value will be the output. So I'm declaring an empty dictionary outside the function. First, instead of returning the values directly, I will assign these to some variables. Nothing changed in the function yet, but before returning the answer, I will first save that into the dictionary. Key will be the input parameter and value will be the answer. So is that all? No, we are storing the result in the dictionary, but we need to change the logic of the code as well. When function is called, the function should first look into the dictionary to see if the dictionary already contains the input-output value. And if that is the case, the value will be returned from the dictionary and actual function calculations will be skipped. And if n is not found in the dictionary, these calculations will be done and the calculated result will be stored in the dictionary for any future call to the function for the same n. Here I am calling the function for first 100 values of the Fibonacci series, which previously could not go beyond 35. Let's see that. And see that here, we get the result in no time. That's a remarkable difference we achieved because of memoization. I hope you like that. There is a shortcut as well to add memoization feature in any function, and we don't need to define this dictionary etc. But before that, let's see that we got the remarkable difference with the memoization, but we need to quantify exactly how much is the improvement with memoization. For that, suppose I want to find the Fibonacci number at index 40. Of course, it is not possible to show the complete structure of this algorithm till Fibo 0, so it's just one very little part of that. Recall the sequence of the program is like for this expression, the first term will be evaluated first, which is on the left side, and that is Fibo 38 plus Fibo 39. For that, Fibo 38 will be calculated first, and then so on. Suppose that everything on this left side is calculated, and now the interpreter will go for this term Fibo 38. But notice Fibo 38 is already been calculated here, and this whole right side needs not to be evaluated because we have the Fibo 38 value. Not just that, in fact all right branches even on the left side are not needed to be calculated. See that we need Fibo 39, Fibo 38, Fibo 37 and so on, and these are the leftmost nodes of this structure, and everything else is already calculated, and if the memoization is used, that needs not to be calculated. See this complete structure of Fibonacci number at index 7. Without memoization, we need all node calculations, which are 25 in total. And with memoization, we need just these nodes calculations, which is 7. For index 7, we need 7 calculations. And to find Fibonacci number at index n, we would need n calculations. So the order of the algorithm with memoization is n. And the order of the same algorithm without memoization was 2 to raise power n. If n is 100, order n computes to 100. And order 2 to raise power n computes to this big value. See the difference memoization created. Although this number does not show the exact number of calculations because left side branches are shorter, but even if we remove those from this number, the difference is humongous. Now let's see the shortcut to implement memoization on any function. For that, I will remove this manual way of memoization and will change the function to its original state. Now to add memoization to this function, we need to import a function LRU_cache from the module func_tools. LRU stands for least recently used and cache means storing. Then we need to decorate our function with this function LRU_cache. In case you don't know about the function decorator, it is a way to customize some existing function with another function. We will see the detail of function decorator at some other time. Here we just need to decorate our function with this function LRU_cache. And that is done with @ symbol followed by the decorator function name on the line just before the function we want to decorate. So by this little addition, memoization is added to our function. Let me first show you again the output without memoization. You can see the output is quite slow. We cannot wait till 100 values, and I will press Ctrl+C to end it here. Now I will uncomment this and will run the same code again. And see that we get the complete result so quickly. We can set the value of maximum size of the cached value by setting the input argument max size. This is the number of recent call results it will be storing. The default value is 128, which is reasonably enough. But if you want to change that, you can set the value here, for example 1000. I will remove that since default size is sufficient enough. Let's compare again the recursive approach and non-recursive approach. We said that recursive approach is simple to implement, but it was very costly, and we resolved that with memoization. So now both recursive and non-recursive approach are fast, but let's compare which one is faster than other. For that we can record the execution time of both approaches. To measure the execution time of a statement, we can use the timeit function available in the timeit module. In this function, we have a parameter stempty for statement, and we have to pass a valid statement as a string, for example print hello. Then another parameter is number to specify how many times we want to execute the statement. The default value of the number is 1 million, so I will change that to just 1. And we get this time value for the execution of this print hello statement. You will get a different value. Even if I run it again, the value will be slightly different because time of execution of a statement depends on many factors like present usage of CPU and memory. So let's print the execution time of both recursive and non-recursive functions. As statement, I will create a list of first 100 Fibonacci numbers using the recursive function first. And we have an error that this function is not defined, although we have defined the function. The reason is that we pass the statement as string input argument, and that is executed by the function timeit in timeit module. But timeit module does not have the definition of the functions used in this statement. The solution is to use the optional input argument globals, and we can pass the complete global scope of this program so that everything here will be passed to the timeit module. We can get the complete global scope of any program using the function globals. Now there won't be issue, but let's also do the same thing using the non-recursive function for the comparison. So the recursive function took almost 0.2 milliseconds and non-recursive function took almost 0.8 milliseconds. So with memoization, recursive function is taking lesser time as compared to non-recursive function. We said that with memoization, the complexity or the order of the recursive function is order n, which is linear. And can you find the order of non-recursive function? For any value n, we have a for loop doing the calculations n-1 times. So maybe we can say that the order is n-1, but that is same as order n. Because the order n-1 means it is proportional to n, and that is same what is meant by order n. We might discuss these details on order at some other time, but here both functions are of order n. Which means that the number of calculations increases linearly with respect to n for both functions. One calculation of the non-recursive function is taking more time than one calculation of the recursive function, and hence the total time of execution of the non-recursive function is higher than that of the recursive function. Now the next question is that is this memoization only possible with the recursive function? The answer is no. We can apply this on any function. Let's do that on the non-recursive function. Over here the function is being called on value from 0 to 99. No value is repeating, and in function body as well the function is not called again as we have the case in the recursive function. So essentially with this use there is no extra benefit of the memoization since the function is not repeated on any input value more than once. Let me just remove the recursive function and let's focus on the memoization on non-recursive function. Now instead of this statement, if I just have a simple statement of function applied on single value 100, but number of times I want to execute it is 1000. Now there will be advantage of memoization, because without memoization, the function will be evaluated 1000 times for the value 100, but with memoization, it will be evaluated for the first time, and in remaining 999 times, it will be picked from the cached result. Let's run it first without memoization. It took 0.0186 seconds or 18.6 milliseconds. Now let's run it with memoization. And now the time is 0.1 millisecond. So 18.6 milliseconds versus 0. milliseconds is a big difference. So I hope both concepts of recursive function and memoization is clear by now. But there is one more thing related to recursive function that you must know. For that, let's see the recursive Fibonacci function and let's print the value at index 499. We get this much big number. Now let's check the next value, which is at index 500. And this time we get an error named as recursion error, maximum recursion depth exceeded. Now what is this error? For that, I will illustrate what happens at the backend when a function is called. All programs use memory of the computer or RAM for the execution. One part of the memory is known as call stack or simply the stack memory, and it is used to handle the function calls. For example, here we have a test function. Interpreter will execute line number 3 printing hello. Then on line number 4 the function is called, and interpreter will move to the function and will execute line number 2. And after that it will return back to the line number 4 where the function was called. But how the interpreter remembers that it has to return back to line number 4? Actually, whenever a function is called, there is a couple of information which will be stored on the stack in the form of a frame. The information includes name of the function, values of the all input arguments, etc. But most importantly, it will store the return address, which is the address of line number 4 in this case. When the function will complete the execution, the return address will be picked from the stack, and that's how the interpreter will be able to land on the exact line where it was called. Once returned, the frame will be removed from the memory. Now see this case where we have function test, and that in return calls the function test2, and test2 calls the function test3. Now when the function is called on line number 8, interpreter will jump to the function on line number 6 and will store the different information on the stack including the return address, which is address of line number 8. On line number 6 the function is calling test2, so it will not return to line number 8 but will jump to the body of the function test2 on line number 4. Again it will store the return address, which is the address of line number 6. Function test3 is called on line number 4, so again all information of test3 including the return address will be stored, and interpreter will jump to the function body on line number 2. It will execute that and there is nothing more there, so it will pick the return address from the stack and will come to the line number 4. Now this frame is not needed and will be removed. Now test2 is also executed completely and it's time to return back where it was called. So the return address from the stack will be picked and interpreter will move to line number 6. This frame will be removed from the memory. Then on line number 6, function test is completed and now it's time to return where it was called. Again the return address will be picked and the interpreter will move to line number 8. The point to notice is that if a function is called which in returns calls another function, that in returns call another function, then all information of these functions will be stored on the stack and cannot be removed until the starting function returns the value. So in case of recursive function, the same function is being called again and again and again, and all the information including the return addresses are being stored on the stack, and that can use a lot of stack memory. So Python puts a limit on the number of inner calls on recursive function. We call that as recursion depth. That's what this error indicates, that maximum recursion depth exceeded. What is the value of this recursion depth limit? We can view that by importing the module sys. Inside the module we have a method getRecursionLimit which will return the value of the recursion depth. And the value is 1000. It means maximum 1000 inner calls to a recursive functions are allowed. In this recursive function, basically double recursion is involved. So that's why for value 500, there are 1000 inner calls needed to calculate the value, plus one call when the function is called first time, making total inner calls 1001, which exceeds the limit. There is also a way we can change this limit value. For that, we have a method in the sys module as set recursion limit. Let's set the value just a little more than 1000. And this time, instead of recursion error, we got the result. So in case you know the recursion depth will be high, you can change this limit to some bigger value, but generally it is sufficient. So that's all from this lesson. Thanks for watching.